So our next presenter, Shyla Liebscher, thank you, comes with another perspective. We've talked a lot about the importance of right-of-way, the importance of being able to put these systems where we need them, where we believe they should be, not just where someone else says you can put them. But that's a tricky proposition sometimes. So when Shyla kind of sent in her proposal, she said that her focus is really on using technology nowadays on siting. How do you use the advanced technologies we have now to put these systems in the best place for many, many different reasons? So she comes with a background on GIS, analytics, geographic information systems. She's been doing that for almost the last decade. Is certified in this technology and has been working with ET3 specifically to help with the issues around siting those systems. So, Shyla.
Okay, great. Thank you. Thank you. So what can transportation do for your GIS network, or for your network? What can GIS do? We've talked about biking. We've talked about trams, gondolas, and tubal transport. Topics of discussion. What is GIS? What are the capabilities of GIS? How can GIS solve your transportation issues? And finally, we'll look at a case study of what I've done for ET3. And GIS, basically, it makes you rethink what you previously thought before. It puts a visual aid to your tables and numbers and allows you to think outside of the box. So what is GIS? You can read the definition up there, but basically it's making maps and analyzing data. There are several types of data that you can analyze, and we'll discuss that later. It examines the impacts of individuals in society and geography, cultural influences of society, current and historical, the qualitative and quantitative aspects of these implications, and the effects of the change factor to the environment. It uses theories, methodology, technology, and data for understanding these processes, relationships, and patterns in a spatial aspect. There are several major GIS software companies out there. The most notable is Esri. They dominate the US. There's Blue Sky, Intergraph, Quantum, Google Earth. And all of these share common aspects. They're all tied to a specific location on the Earth's surface. They all operate using a centralized database that you extract the data from and display in a graphical user interface. And they all consist of layers and data. And there's several types of data. And the layers are just the files as you add them into the map. And GIS represents an exciting and rapidly expanding technology via which spatial data may be captured, stored, retrieved, displayed, manipulated, and analyzed. And I kind of talked to some of y'all about that using the different software platforms last night with the maps that I have out on the table. If y'all haven't gotten a couple of them, you can grab them. The capabilities of GIS. You can create a central database of files. You can store, analyze, and create data in a variety of formats. It's distributable. And you can share it on the web. So anybody can see what you're doing. You can share your data. So the database of files. You can create these for project-specific areas. You can track factors of change in the database. And you can have a master database of files that you import your project-specific area databases to for easy access throughout your organization. The variety of formats you can do alignment sheets, which is typically what you see in construction projects. And exhibits are like the information that you submit to the government because they don't want to see all that technical detail. They just want a pretty little picture that they can look at and go, okay. You can also do charts and graphs from your data inside without having to open up Excel. Then you can export it to PDF, Excel tables, images such as PDF, PNGs, JPEGs, JPEG 2000s. You can do AVIs, those are movie files, all kinds of stuff. So you can do like a movie of your GIS going down your transportation network system. This is an example of a sample alignment sheet. Distributable. These files, you can distribute them pretty easily because you can export them pretty easily into different formats. You can distribute them by email in a shapefile format, or you can put them on FTPs so your clients can grab them, or anybody around the world can grab them, especially a lot of y'all travel a lot. So you can easily access them. You can have them on your local drives on your computer, or you can serve them up over your IT system and in your organization. The new rage is a cloud server. The ArcGIS, Online, Google, and Amazon notably are some of the biggest ones. And this reduces your costs because you don't have to have in-house storage and you don't have to follow all the guidelines for that. They take care of it for you. Or you can create your own API. This is a web map where people can log on and they can do limited amount of their own GIS work. So they can pull up the files, they can extract the files, they can do minor editing if you choose to give them that capability. If not, they can just draw graphics on the web API, and then that would be updated by a GIS analyst in-house. And these can be accessed by virtually anyone, your own personnel, your clients. You could put it up just on a website so people can come view it if they want to see what you're doing, if they're interested. More analysis capabilities. They can perform complex mathematical functions. They spatially tie in non-correlated data. And they can create a time series for predicting future events. And I'm going to show you a little 2-minute quick video of what GIS is all about.
A geographic information system uses computers and software to explore the fundamental principle of geography, that location is important in people's lives. GIS is used to inventory, analyze, and manage many aspects of the world. When you flip on a light switch, chances are a GIS helped make sure the electricity was there. If you drive down a highway, chances are a GIS managed the signs along the way. And if you look at a map on the internet, chances are a GIS helped make it possible. A GIS takes the numbers and words from databases and puts them on a map. Much information is tied to a location, and a map shows patterns in the data we might not otherwise see. GIS allows you to use your existing data in new ways. Putting data on a map helps you ask questions like where, why, and how, with locational information in mind. With geographic knowledge, you can make better decisions. With the vast sources of information available today, GIS is a key tool in determining what it all means. GIS can make maps coded by values from the database to help illustrate patterns. For example, to better understand traffic accidents, we might first group collisions by police grid, then as hotspots. Finally, we can show where citations are issued. Another look at the same data can show accident locations over time. GIS provides location-based solutions today for government and industry around the world.
So gains in both employee productivity and transportation system performance are made possible by the unique ability of GIS to integrate with a variety of systems and technologies. They benefit by making use of the resultant information throughout their enterprise, and it just aids in better decision making. Most people are visual. When they see a picture, they have that aha moment. If you give them a table, they kind of get lost in the numbers, and it just makes it easier to make your decision. And how can GIS help you? It's a great tool for visualizing concepts. It has many value-added business functions. You can, like I said, you can store your qualitative and your quantitative data in there. You can store personnel database. For example, BP is using GIS as an automated alert system. So when a hurricane comes out in the Gulf, they know exactly which employee is on which rig, and they can send a page to that employee saying, you're about to be evacuated. And they can get ready. So they don't have to go search and just call everyone to see who's where. and they save time and money by just effectively communicating with the personnel that they need to. Routing the system, design. This will tell you where is the system, what is the feasibility of the system, risk assessment and management. You can also do transport, you can do shortest path, you can do scheduling, you can do networking. So shortest path would be the fastest way to get to A to B. Scheduling would be for automated transport. So you could use the GIS to tell you, okay, this car is here and this car is here, and it will be leaving here. And you can keep track of all of that in the database, all while storing that data to recall for later purpose. And networking would just be connecting this. How would I connect my systems? Where would be the best locations for that? Some of the complex mathematical functions that it can handle, and these are not, it's not limited to just these. It's a vast amount of math that you can do in there. So Euclidean distance, that's just the ordinary distance that one would measure with a ruler. It's used the Pythagorean theorem for that. Line of sight, it would be if you're standing on top of a mountain to another top of a mountain, what would be the clearest visual path so you wouldn't have to cut down trees or nothing obstructing your view. Spread functions, it's the best way to get from point A to point B with a given set of variables and constraints. Map algebra is a set-based algebra for manipulating geographic data. Slope, we all know what that is. And it's models. Basically, you can combine a number of these mathematical functions to produce an output and an expectation of what you could likely see happen in the real world. The statistical analysis functions, classification, cost analysis, queries, and sampling. So classification would just be grouping a like set of variables together or a like set of data. It's not limited. You can control that. You pick which way it samples. You could do a manual. You could do a best fit curve. It's really unlimited. You can set your number of classes. Cost analysis, you could use this to determine what would be the cheapest path for me versus what would be the best, so you can get the highest return on investment. Queries, that basically allows you to just pick a subset of data and run your analysis on that. And sampling is creating random points from a given set of points, and this is usually done with rosters. Rosters are an image format that GIS can handle. So when you go to Google Earth, that's what you see. It's comprised of billions of rosters from all over the world, different government agencies. Everybody kind of contributes to that. And if you look really closely in Google Earth, when you zoom in, you can see it's either in the middle of the screen or the bottom of the screen, depending on your operating system. It'll tell you where that data came from and when it is. You can also run a time analysis. You can go back to see 1950 imagery. You can see 1975, how far back you want to go. Unfortunately, you can't go forward because we haven't done that yet. But it's great for historical analysis. Spatial correlation. That's the fun part. You can do density, interpolation, georeferencing, geocoding, and COGO. So interpolation is the process of using known values to estimate the values of other points which are unknown. It's kind of like sampling, but that's with vector data. And vectors are just lines, polygons, points, anything that's not an image. There's, I think, like 9 types of vector data, but most commonly you're going to look at points, polygons, and rosters. Some basic types of elements of COGO are points, spirals, lines, horizontal curves, and circular arcs. Some more complex elements can be developed, such as alignments or chains, which are made up of a combination of points, curves, or spirals. Time analysis. This is really cool. That's what I was talking about in Google Earth. So you can look at historical, future, and trends. Okay. For example, how many people were using this system in 1950? How many writers are currently using this system? How many projected are to be using it by 2020? Demographics. These are things like where should the system sit? Which communities will benefit? How will you select where the system should go? How will it change the community? Will people move to be closer? And those are just some of the types of questions you can answer, really anything that your mind can imagine. And you look at track factors of change and stuff like that. So ET3, a case study of GIS and sustainable transportation. And this just highlights what some of the stuff that I've been doing for ET3, what I hope to see ET3 implement, and what they also hope to see ET3 implement. So we're using it for permitting, analysis, facility design, right-of-way determination. We hope to use it for stabilization and rehabilitation, regulation and governmental agencies, and metadata and documentation. So permitting, that would be like your, everybody knows about the Las Vegas tube. It sits on 1.3 miles of BLM land, so we have to apply for the BLM permit. And part of the permit is they require a GIS map of where the system will sit. Analysis, we're using that to follow the ET3 constraints, but I'll highlight that a little bit more later. This is an exhibit, an example of the UK map. You can find it on Facebook, and there's a couple of other websites. Alignment sheets for construction, so once we start building, we'll need to, the initial exhibit will go to the BLM application. Once it starts to be built, we'll have to send alignment sheets to update them on the status of how everything is going, and elevation profiles. So we'll be able to see exactly what the system is going to look like from an elevation standpoint. Analysis, we do passenger comfort, which is one of the main factors ET3 is concerned with. We don't want people getting sick. Environmental impact, how will this affect the environment? You know, especially since we're going to be sitting on a BLM land and it's close to a park. Is it going to affect migratory bird species? Are there certain plant life on the right-of-way that can't be disturbed, protected species, stuff like that? Mitigation is how will you handle the impact of putting this transportation system on the property? Will it affect the water flow, the surface water flow? More concrete, obviously you have less drainage and you have to find a place to put that water. That's the main focus of what mitigation is. And demographic analysis, you know, how will people actually be using this? You want to put this in a place where you're going to get the maximum benefit from it. You don't want to put it in an area where nobody goes because nobody's going to use it. So we used census data for that. It can also aid in storing locations and data about the support poles, the portals, parking lots, storage center areas, power stations, emergency road routes, any other major structure that they need to maintain a location on. You can, as long as you have an XY for it, which you can get for everything because everything has a location on the Earth's surface, you can put it in a map. Right-of-way determination, route analysis. So some of the ET3 constraints, basically, I'll give you a few numbers. So if you're looking at a 350 mile per hour system, you have to have a curve radius of 9,000 feet, and your acceleration and deceleration rate is half of your curve radius. So basically how long it's going to take you to get up to 350 miles per hour, and how long it's going to take you to slow down from 350 miles per hour. At a speed of 700 miles per hour, you have an 8-mile curve radius with a 4-mile acceleration and deceleration. And obviously, as you get faster, those numbers become larger. At 4,000 miles per hour, your curve radius is 206 miles. And so you're looking at 103 miles to accelerate and decelerate. And that's the demographic, that falls back into the demographic analysis. Some of the issues that we're having with the United States is up in the north, some of those cities are so close together. So if you have the 2,000 mile per hour system, you have to maintain a curve radius and an acceleration and deceleration. When you're looking at cities that are only 40 miles apart, you're going to have some serious issues of getting people on and off of these systems. So you kind of have to pick, you have to use traffic counts, determine how people move, because you don't want to just try to hit every city because it's impossible. Also, up north in the Dakotas and stuff like that, you don't have a lot of people generally. They're very spaced out. So you don't really want to put a lot of systems. We don't want to put a high-speed system up there because it's expensive. So you would want to maybe have the smaller system go out there, the 250 mile per hour system, something, you know, that will probably more get used. Cost analysis, what's going to be the highest return on investment? If you're obviously going over hills and mountains or through fault lines, you're going to have more stability, you're going to have to apply, you know, more precautions, and elevations, you're going to have fewer poles in between, stuff like that. So you want to get the highest return on your investment when you're building this, and this can help you do that. You can run a cost analysis by associating what's the word? Basically, you can put a function in there that says, for every mile that you build, it's going to cost this. And you use that by determining the cost of materials and stuff like that, which ET3 already has. And you put it all together, and it says it's going to cost you $50 million to build this pipe. And you know, you can kind of figure that out with GIS, but you can get a better perspective on it of what it's really going to cost. And you can account for, you know, damage of materials and stuff like that. So you can add a 10% markup to it if you want, and apply that, you know, if something were to happen, if some pole were to break, or, you know, a piece of concrete got a crack in it or something like that. You always want to account for that kind of stuff when you're building a system. Surveys, GPS. Everybody kind of knows what GPS is. So you would go out there once the system is built, and that's what you base your alignment sheets on. And you could just use a little handheld TomTom. You can use Pathfinder, a Trimble. That's standard what we use in the oil and gas industry. And Arc, or Esri also has Arc Mobile, so you can basically run ArcMap on your iPad or your tablet and go out there and update and edit on demand and send it back to your organization home and update. They can update the database real quick and have it right back out to you in less than 10 minutes. So you don't have to send another person out there to do it later. Centerline surveys, that's what you base, that's where you get your GPS points, and then you create a centerline. Meets and bounds, those are just survey descriptions usually required for governmental agencies. And they're long and boring, so I won't bother you with what those are. Stabilization and rehabilitation. This is one of the biggest things. FEMA uses it, uses GIS to plan for hurricanes and what they would do in a natural disaster. You can fire, flood, tornado, hurricane, any kind of natural disaster. Somebody had asked a question in ET3 about bullet holes. Well, you could run a model to see what would happen if somebody were to puncture the tubal system and determine, okay, this is what would happen, this is how we would respond. You could see, you know, if there was going to be an issue, an unforeseen issue, that, you know, since ET3 has never been built and never been punctured, you know, we could conjecture all day long. But in GIS, you could actually run an analysis and have a fairly accurate assessment of how and what to do in a situation like that, and how the apertures would act when the air comes in, stuff like that. Just test your theory, so to speak. Regulation in government agencies, and a goal to self-regulate. ET3 is working on this. They want to have a master database of files, and we plan on submitting updates every year. Of course, the system's not going to change, but it's kind of a standard policy to go out and remap everything every year. And so what you would do is you would just send somebody out there. They would take the GPS points, upload them, verify that everything is still the same, print it off, send it to the government. So then you don't have to worry. And you can do that on a federal, state, and local level. You can send them all the same documents. You could have templates for each regulatory agency that you have to deal with, because often they have their own specific formats and templates that they like to see the data in. Metadata and documentation. This is one of the biggest things in GIS, because everybody wants to know where did the data come from? How did you come to this conclusion? Is the science sound? And we have something in GIS called verifiable, traceable, and trackable. And it's a history of all the data that the GIS is used to determine any form of analysis and decision and documentation created, and it's all stored in the file through the metadata tool. And you can hold things such as, we got this file from NOAA, and it stores on its own, this edit was in an XML file, this edit was run at this time, and this analysis was performed, and this was the conclusion. So you just click on the XML file, and it pops up, and it'll show you attribute changes, analysis, when it was added to a map, when it was transferred from one disk to the other. I mean, you can track everything. So that way, when somebody comes and says, well, how did you do this? You can say, I did it just like this. And that's it. Any questions? Thank you. Thank you. Google. Yeah, and you can download that for free. It's really fun.
What other websites are you using in your GIS world?
I use everything. If I can't find it, I will go make it. ArcGIS Online, if you want to go learn, they have a free online web API that you could just create a user account, and you can go build your own maps in there with pre-existing data that people upload themselves. They create their own layers and add it to ArcGIS Online. Government agencies, so the UN Sustainable Development Board is what I used for that giant map. The federal government website is where I got the bike data. Existing files, just PDFs, georeferencing, I had mentioned that. So a lot of the times when we're doing pipeline assessments, these pipelines were created 50, 60, 70 years ago. And so all we have now left is the paper copy of the original construction. So you can scan that in your printer and save it in an image format. You can upload it into your GIS, and you just find out where it is based on the coordinate system that the original document was done in and what you're doing, and you apply a transformation, and it lines right up. You just add your control points, and you have the picture, and you can trace the picture onto where you need it to be on the Earth and create a vector format for it. Really, GIS can handle, it has to handle specific file formats, but since it's underlying, what word am I looking for? It's based on access. So anything in Access, anything in Excel, if you can make it into a table, you can bring it into a GIS. And it has to have a unique ID. Yes? Yeah, well, there's several different kinds of elevation data. There's LIDAR, which is the most accurate, can see through treetops. There's DEMs, there's national websites. For Texas, which is where I'm from, we have TENRIS, and it's the Texas Natural Resource Information Systems. And they have DOQQs, they're digital ortho quarter quads. So they're pictures of the ground. And you can go download anything that you need from there. And they're updated on a yearly basis. In Houston, which is where I'm specifically from, we have the Houston Galveston Area Council. And they spend about $2 million every year flying over Harris County and the 9 surrounding counties. So they collect new imagery every year, and they upload it onto the website. And for a fee, you could pay, and you can have access to this brand new data every year. Nevada also has a site like TENRIS where you can get the digital elevation models for that, the DOQQs. So yeah, and it depends on your source. Obviously, like Houston, where they update it every year, you're going to have the freshest digital elevation models. TENRIS, not so much. They rely on places like HGAC to provide them with the new updated files, which could take, 1 or 2 years. Google Earth, you can get the digital elevation models from there. You can extract it. But the way that Google Earth, they work in partnerships with people, and so they offer them a license for their aerial imagery. So, you know, you may have one county where it's brand new, 2012, 1 meter resolution imagery, and then the next county over may be from 2006 or something like that. It just depends on how they participate. Optimally, you want the freshest satellite data. So you would go with a LiDAR company and you would probably want to contract it out. It's getting cheaper and cheaper nowadays. And I know there's a couple of organizations out there like GeoEye, where because they're one of the largest providers of aerial imagery. And so they're contracted out to do different surveys, aerial surveys for different companies. And once they do that, they own the data. And so they have a master database. And for a small fee, you can go and you can access all of the aerial imagery even that they've done for other companies. Yes, well, really what determines above ground and underground is the speed of the system. But once they've determined whether or not it's going to be above ground or underground, you would just acquire the seismic data that you need, and you could run analyses. It can work above ground, below ground. It can work up in space. Anything that can be tied to a location, basically. So underground, what you would have is a negative elevation model for that. So instead of, you seeing like this is 32 feet, you would see negative 32 feet. And so when you see a negative sign for an elevation, that's how the software would recognize that it's underground. Yeah. Well, actually, there's the National Soil Surgo-Set. The Surgo-Set, it's the Soil Survey. Go away. I can't exactly remember what the acronym stands for, but it's the National Surgo-Set, and they have all of the soil data already mapped out and available for purchase. And sometimes you can acquire this data for free if you do the right research and know who to get in touch with. So a lot of it's out there, and that would be a contributing factor. So a 2,000-mile system underground, obviously it's going to be more expensive to drill through bedrock than it is if it's clay or something like that. So yeah, that would help in determining that as well at that point. But the initial step would have to be, do you want it above ground or underground? And then you would do the analysis. Think of it as like the scientific process. You ask the GIS. You want to know an answer to a question, so you ask the GIS a question. The GIS runs the analysis and it spits out an answer for you. Is that it? Okay. Any more questions? Anybody? Bueller? Thank you.